Hello and welcome to this video. In this video we are going to be looking at the practical of the inverse square law for nuclear physics. So this is another one of the practicals where you aren't going to be looking for an exact value or calculating any kind of result at the end of it. We're again just trying to prove that a trend is true. Now what we're trying to prove is that the intensity of radiation, in this case we have to be specific, intensity of gamma radiation is inversely proportional to the square of the distance from the source. Now, so there's a very important point that I just stated, has to be gamma radiation. Okay, now the reason it has to be gamma radiation is because that is electromagnetic radiation. That is a wave. And so it will happen spherically. Okay, so you'll end up with this kind of radiation being emitted everywhere, and the intensity of that radiation is going to be measured as the power divided by the cross-sectional area. Okay, and this is why we get that inverse square relationship, because we know this area is going to be due to 4 pi r squared if this is the surface area of a circle. However, we don't need to know this part. What we need to know is how are we going to do this? How do we actually prove this relationship? And so in everything we have to vary one of them, measure the other one. Now what we are going to do is it's really easy to vary the distance. Okay, so we are going to vary r and at the same time measure the intensity. Now intensity itself probably isn't going to be the easiest thing to measure, because we would have to get something that can measure the amount of energy that it's transferring per second, and then we'd have to know the cross-sectional area of the detector, and then that would give us our intensity. What we're actually going to do instead is measure the count rate, since I can say that the count rate is going to be proportional to the intensity, because the higher the count rate, the more radiation is being given out per second, the more energy is being transmitted. So what I'm going to do is I'm going to say let's have this here as my radioactive source. Now this is going to be a sample of some radioactive isotope that we know is going to give out gamma radiation. Now we're going to put this in a lead box, because this is obviously very dangerous. We don't want to be exposed to too much gamma radiation. So we put it in a lead box with a little slit opening here, so that the lead box will absorb all of the radiation except the one traveling in this direction. So it will allow gamma radiation to travel out just in that direction. And what we need to do then is we need to place some sort of detector at this position in order to detect all of that gamma radiation that's coming out. So we're going to put a Geiger counter here, or a Geiger tube here, and this tube is going to be our detector. So this is a Geiger tube. Now the Geiger tube will be connected to a device that will keep count. So this is going to be the counter. Okay, and this will then have a display that will then produce some count of how many bits of radiation does it detect as long as this keeps running for. Now we obviously then need to measure the distance, because our whole relationship is going to be between the count rate and the distance. So where we measure the distance from does actually make a difference, but not to the proportionality, right? It doesn't really matter as long as you stay consistent whether you measure your distance from the entrance of this box to the very start of this tube, or the entrance of this box to the very end of this tube. It doesn't matter as long as all of your measurements keep that same convention. Okay, so what we're going to have is a ruler. If you have access to like good lab equipment, you might be able to get a sliding ramp that will actually have a distance scale across it so that you can slide your detector across, and so you always know that you're in this kind of line here where the radiation can reach that, because if you were to move it by some degree, either way you'll probably end up not covering the full face of the detector. But this is then if you have kind of a low budget, I guess. This is then going to be just your ruler that's going to measure the distance. And what I'm going to say for this video is I recommend going from the very edge of the box to the very start of the tube, and we're going to call that distance R. Then what we're going to do is we're going to vary R, so we're going to vary it so that we can count the amount of radiation detected at each of these distances. Now, we need to, our whole point is we're trying to get a count rate, which means we also need to set up a timer, and that timer needs to be set to the same time each position. So what we're going to say is we set to a position, and then we start the timer and the counter, and in order to get from the like when the timer's up, so the timer maybe lasts for, I don't know, 1 minute, 2 minutes. Again, this information will be given to you by a supervisor. I'm going to say let's just have this per minute, okay, because that way you're not waiting around for too long for the counts to be taken. And so we leave this in each position for 1 minute, and we take the amount of counts or the display that the counter gives. We read that amount for each position, okay? Then we need to make sure that we're converting from the counts to the count rate. And the way we do that is we say count rate. The word rate, we should remember, just means per unit time. So it's the counts divided by 60 in the case where we have 1 minute. Obviously, if your time is different, if you had 10 minutes, for example, you would do the counts divided by 600. Okay. Then we now have the count rate. However, this isn't going to give us the correct value, because not only do we have the radiation due to this source, we also have radiation due to the background radiation. And so the background radiation we then need to take into account in order to calculate the corrected count rate. Now, the background radiation is where I'm going to have another Geiger tube, but I'm going to face it a different way just to prove that it doesn't, or it shouldn't be pointed towards the same radioactive source. So I have some other Geiger tube connected to another counter, and I am going to leave this in the background to run for 10 minutes, right? So it runs for 10 minutes, and all this is going to do is basically then calculate or measure the amount of radiation due to the background radiation, okay? And the reason I'm running this for 10 minutes is just to make this a more accurate value, because I'm going to have to apply this across every single measurement that I take of the counts. Then from this part again, I'm then going to say that my count rate due to the background radiation is going to be the number of counts that I get from this Geiger counter divided by 600, or 10 minutes. I want these count rates to be per second, okay? Then I will again do this for each of these different distances, and then I can calculate my corrected count rate, so the actual count rate that I'm going to plot, which is then going to be, so the corrected count rate is going to be the count rate due to the actual reading, so the count rate that I read minus the background count rate, okay, because that means that I'm then taking all of the radiation that I've received, and then I'm getting rid of anything that's due to background radiation, just so I can narrow it down so it's just the gamma radiation that's coming out of this radioactive source in this lead box. Then, from this point, we can make our table finally. So we can say that our table needs to first include the distance that we have measured. So this is r, and we're going to measure it in meters. Then we're going to measure the counts, which is just a value, so it doesn't really have any units. Then we're going to measure the count rate, so we're going to convert it to a count rate. Then we're going to convert it into a corrected count rate by minusing the background radiation, so the corrected count rate. And then we can make our graph. We're going to use these values. We're going to plot the corrected count rate against the distance. So this here is going to be the corrected count rate against the distance r. Okay, now what we're expecting here is actually we're trying to prove a relationship that the intensity, or in this case the corrected count rate, is proportional to 1 over r squared. So if I were to do it like this, I would end up with some kind of graph that looks a bit like this. What I actually want is a straight line graph as usual, so I'm going to plot this against 1 over r squared, and this should give me a straight line. Now, this straight line will not go through the origin of your graph, okay? It will be a straight line. You should end up with a linear line, which then proves this relationship. However, you have got something where our distance r is never going to be accurate using this method, okay? Because our count rate detector, this Geiger tube, the tube contains the detector, okay? Now the tube has some length, and we're always taking the measurement either from the end or the beginning. You could take it from halfway, but that would make it less accurate. But the detector could be literally anywhere inside this tube. So maybe in some of them, the design is that the detector is right at the end of this tube. Maybe sometimes the detector is right at the end of this tube. Maybe it's here, maybe it's here, maybe it's here, right? We don't know. Either way, we're going to have some offset that is going to cause 1 over r squared to shift so that we don't get an exact 0. However, this isn't the only reason it doesn't go through the 0 point, because we also have the fact that this radioactive source is the 0 point for the distance, but we are measuring from this point. So we've already got this offset as well. So we're actually going to get multiple offsets. So this is why the 1 over r squared shouldn't go through the 0 point. However, doesn't matter, because we're just basically trying to prove that this is a straight line graph, which proves this relationship, and hence we've proven the inverse square law. Now, a second problem that you could come across is the fact that maybe for smaller distances, you're not going to get a complete straight line. Okay, so issue may be that for small r, you end up with a non-linear relationship. And this is common. This would make sense because we know that this gamma radiation that is being given out is subsequent based on alpha or beta radiation being given out first, which means if we get closer, a Geiger tube doesn't care what kind of radiation it absorbs, it just cares that it's absorbing radiation. So if you get closer, it means that you're going to also absorb or also detect some alpha and beta radiation, and that is why you're going to end up with, if you go to maybe a few 10 centimeters, maybe a few centimeters, the closer you get, the more non-linear your curve is going to get. This is why you probably want to take values. So to correct this, you want to take values from large distances. Okay. Now, when I say large distances, I mean maybe 1 meter to 2 meters. Okay, you obviously don't want to go 50 meters away because then you barely detect anything. Okay, you still want to make sure that you're getting a decent variety of readings. So you want about 6 measurements from between 1 meter to 2 meter, and then plot your graph from these measurements. Okay, I've only introduced this stuff at the end to prove to you that this experiment isn't a perfect way to prove this relationship, but it works. Okay, and these are some of the problems that you can encounter. Thank you for watching.